In this class, we will discuss the S.I and Gaussian unit and dimension of the three magnetic vectors, namely vector B, vector H and vector M. And we define vector B to represent magnetic induction, vector H to be the magnetic field, and vector M standing for magnetization, also called the magnetization vector. Let us write down how these three vectors are interrelated in SI system as well as in the Gaussian system, and then we will proceed to find the unit and dimension of these three quantities in the two systems. Interrelations, we write down the SI equations here and equations in the Gaussian system here. In SI system, these three vectors are related as vector H equal to vector B by mu 0 minus vector M. While in Gaussian system, they are interrelated as follows. Vector H equal to B minus 4 pi vector M. It follows from this SI equation that the dimension of H, the dimension of B by mu 0 and the dimension of M are same. So H, B by mu 0 and M should have same unit and dimension, as evident from this interrelation. But in Gaussian system, this is the interrelation from which it follows that H, B and M all have same unit and dimension. Let us proceed to find the unit and dimension of the three vectors B, H and M and verify whether these statements are correct. Let us first find the unit and dimension of B in SI system. Vector B is defined from this relation vector F equal to Q into V cross B, which is the Lorentz force relation, from which it follows that B goes as F by QV. F is force, Q is charge moving with velocity V, so we can replace V by L by T, and again Q by T is I, so that this gives F by IL. The unit of B is therefore, instead of force we can write Newton, instead of I let us place ampere, and for length we have meter. So this is the unit of B in SI system, which is also called Tesla. Let us rewrite B equal to F by IL, and use the fact that energy is power into time. And energy is force into distance, and power is current into voltage, and T for time. So from here, F by I is Vt by L, and here we have F by IL, so we can write Vt by L square, because we have multiplied the denominator by 1L, so it becomes L square. So the unit of B becomes volt into second divided by meter square. Let us write in short, volt into second by meter square is the unit of B, also called Tesla. To find dimension of B, let us use the result F by QV that we used in the beginning. So the dimension is, instead of force, let us write mLT to the power minus 2, C for Q, and this V, small v, is velocity. So it is, now this on simplification gives us again current is dq dt, so ampere is Coulomb by time, that is second, or A into T is C. So with this we can write for B instead of C we can use AT, and simplification leads to so this is the dimension of B, and so is this one, dimension of B. Having obtained both unit and dimension of B, let us prepare a chart for convenience. We shall write the quantities here, then unit and dimension in SI system, and then again unit and the dimension for Gaussian system. The first quantity we discussed is B. The unit of B is Tesla, which stands for these combination of units. And the dimension is or let us next find the unit and dimension of B by mu 0. But first, we discuss the unit and dimension of mu 0, and obviously in SI system let us recall the expression for magnetic energy density, which is b square by twice mu 0. We note that this represents energy by volume. So the units are force into distance for energy by volume, which is L cubed. Now for B, we got B equal to F by IL. So we can write simplification gives us F by L square, and here we have so what we get from here is mu 0 is F by I square, and therefore the unit of mu 0 is Newton for F and ampere for I square. So this is the unit of mu 0, and we are in a position to find the unit of B by mu 0. Let us put the unit of B, which is Newton per ampere per meter, and that of mu 0 is this one. So simplification gives us, which is the unit of B by mu 0. The dimension is therefore A for ampere, and 1 by meter is L inverse. So this is the dimension of B by mu 0, and if we put I equal to dq dt, that is ampere as Coulomb by time, then we end up with as an alternate expression for dimension of B by mu 0. Let us put now the unit and dimension of B by mu 0 in the chart. The unit of B by mu 0 is ampere per meter, and the dimension is L inverse A, or this one. We now proceed to find the unit and dimension in the Gaussian system of B. So let us find now the unit and dimension of B in Gaussian system. And we start with the Lorentz force, the expression of which is now we note that This V stands for velocity of the charge Q and the C is the speed of light. So when we calculate the unit or dimension, they will cancel out, and what we are left with is B is F by Q. Now this is same as the electric field E, since according to Coulomb's law, in the Gaussian system, force is given by this expression, and F by Q is Q prime by R square, which by definition is the electric field. So we note that electric field is F by Q and so is B F by Q. Hence we state that E and B both are F by Q in the Gaussian system. Now the unit is dyne by StatCoulomb, which is actually Gauss. The unit of B is F by Q. Now by Coulomb's law, it is Q prime by R square so the unit is StatCoulomb per centimeter square. So this is the unit of B in the Gaussian system, which is same as that of E. Now dimension of StatCoulomb was shown in the previous video on unit and dimension of the electric vectors E, D and P to be so we get and centimeter square is length square. So on simplification we end up with so this is the dimension of B in the Gaussian system. Let us put these things in the chart. Unit of B in the Gaussian system is this one, as well as StatCoulomb per centimeter square. And the unit of B in the Gaussian system is referred to as Gauss. And the dimension of B was shown to be this one. So we have got this row filled up. Now mu 0 makes no sense in the Gaussian system, so these cells are not applicable, and we move over to find the unit and dimension of H in the SI system now. So unit and dimension of H in SI system, and for this we have to rely on the Ampere's circuital law, according to which the circulation of H over a closed path is equal to the free current, from which we get H into length is equal to I or H is I by L. So the unit is ampere per meter. So this is the unit of H. Let us mention that current flows in closed loops, and if there are n turns or n loops, then we would be having an n factor here, and then it is customary to mention the unit of H as ampere turn per meter. So this can also be taken as the unit of H. However, for today's purpose, we will use ampere per meter because number of turns has no unit or dimension. Now we come to dimension, which obviously is L inverse A. And let us put these things in the chart to get, for H it will be ampere per meter, and the dimension is L inverse A. And these we find to be identical to that of B by mu 0. We now proceed to find the unit and dimension of H in the Gaussian system. So unit and dimension of H in Gaussian system. For which we have to rely upon the Ampere circuitry law as before, and we get now here there will be a factor of 4 pi by C IF. Therefore H into length is current by speed or velocity. So what we get is H equal to I by C into L. Now this is C is L by T. Again I into T is nothing but Q. So it is Q by L square. So the unit we have got is StatCoulomb by centimeter square for H, which is called Oersted also, and the dimension will be same as that in B, because for B also we got this same expression, and here is what we got. B has unit StatCoulomb per centimeter square, leading to this dimension. So this is the dimension of H, and let us put them in the chart. The unit of H in the Gaussian system is this one, and therefore let us write it here, which is actually Oersted, and the dimension is which is same as that of B. Let us now move over to find the unit and dimension of M, the magnetization vector in the SI system. So unit and dimension of M in SI system. This follows from the definition of magnetization, which is and magnetic dipole moment is current into area, and in the denominator we have volume, so this can be written as I into L square by L cubed. So on simplification what we get is I by L. So the unit is therefore ampere per meter for M, and the dimension will be L inverse A for M. And let us put this here in the chart. Unit is ampere per meter and dimension is L inverse A. We now proceed to find the unit and dimension of M in the Gaussian system. So let us consider the unit and dimension of magnetization in Gaussian system. And this follows right from the definition of magnetization, which is, now in Gaussian system the magnetic dipole moment is current into area by C. So we can write it as, in the numerator and in the denominator we have L cubed, so it becomes I by CL. This, as before, is C can be written as L by T, so that we have I into T by L square, which is actually Q by L square. So as before, the unit is StatCoulomb per centimeter square for M, and the dimension will be this one as before. And let us fill up the remaining cells of the chart. From this chart it follows that B by mu 0, H and M all have the same unit and the same dimension in SI system. So B by mu 0, H and M, they all have same unit and dimension in SI system. We also note that though H and M have same unit and dimension, that of B is different. So we can write that B has different unit and dimension. Of course in SI. And we also note that B, H and M have same unit and same dimension in Gaussian system. So this is a very important conclusion. Again, in the previous video, where we found the unit and dimension of E, D and P, we showed that E, D and P have same unit and dimension in the Gaussian system, and here they are, and we observe that they are same as that of B, H and M, which we found in this video. So we can write E, D, P and B, H and M, these being the electric vectors, these being the magnetic vectors, all have same unit and dimension in Gaussian system. And the unit is StatCoulomb per centimeter square, and the dimension is a very important conclusion.